Hello and very good morning to all of you. My name is Anand Ranjan and I am assistant professor in School of Computer Application, Babu Narsidas University, Lucknow. I welcome you all in the video lecture series of digital electronics. In this video, we are going to discuss about the magnitude comparator circuit. Hello. So, the magnitude comparators are basically the circuits which actually perform the comparison of two inputs. These two inputs will be in either in the digital domain or digital numbers, or some signals we can say that need to be converted in digital for the magnitude comparison point of view. So magnitude comparator, it determines the relative magnitudes of the two numbers. First, we will discuss the single bit magnitude comparator, and then we will discuss the uh, then we will discuss the multi-bit magnitude comparator. So single bit magnitude comparator, the inputs are of 1 bit each, means we provide two inputs and our circuits will actually compare these two inputs. The comparison will be based on whether the one input is greater than to the previous one, less than to the previous one, or equal to the previous one. So this is actually the conceptual block diagram of a magnitude comparator circuit. And of course, these magnitude comparator circuits comes under the combinational circuit design aspect, in which we have discussed that we have to follow the four major steps, in which first of all we have to identify our inputs and outputs. Then we have to construct a truth table which actually tells us the overall operation of the block diagram which we have suggest initially with that inputs and outputs. And then we write the boolean expression for the output, which represents the boolean function of that system. And finally that boolean expression needs to be simplified, either the boolean algebra or the Karnaugh map, and then further the reduced or the simplified expression will be implemented using the basic logic gates. So in this magnitude comparator, single bit magnitude comparator, as we can see here, that these A and B are our inputs, and these three X, Y and Z are our output. If X is equal to 1, this signifies that A is greater than B. If Y is equal to 1, this signifies A is equal to B. And if Z is equal to 1, this signifies A less than B. So based on this conceptual block diagram, we develop this truth table. And in this truth table, these are our inputs A and B, and these are our outputs X, Y and Z. So with the two inputs AB, we can able to generate four different combination, and these are the four different combination for the comparison point of view we have taken. And 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 uh, these are the outputs X, Y and Z. We have select based on the inputs provided to this system. For example, if A and B both are 0 0 and A and B both are 1 1, then in that case we as per the block diagram we can say Y is equal to 1. So we have this Y is equal to 1 1 over here, we write, and the remaining all outputs we put as 0 0. While in the second case, as you can see, A is 0 and B is 1, then of course this is A is less than B case, hence we write Z is equal to 1 case over here, and the remaining two are 0 0. Finally the third one, in which A is 1 and B is 0. So the magnitude of A, you can say A is 1 and B is 0, so A is greater than B. This is the case when X is equal to 1. So in the column X column we write this 1 here, and the remaining two zeros are over. So in this manner we can able to construct the truth table. And this truth table we can say now with this truth table we can able to write the output expression for X, Y and Z. So you can see here we write the output expression based on the min-term approach. Means if, for example, if we take x column, then in the x column we have only single one, and this single one is correspond to a bar, a b bar, a b bar. So this is, we can write over here, x is equal to a b bar. Similarly for y, we have to write that min term for 1 1. This is we can say a bar b bar and ab, a bar b bar and ab. And of course this is a very standard expression, so we can write ax nor b, ax nor b. Another form we can also say that the NOR is nothing but the complement of XOR. So hence we can write in this way also. This will help us in implementing the this single bit magnitude comparator. Similarly, in Z column we have one single one over here, and this one is corresponding to the min term a bar b. So we write Z is equal to a bar b in this. And now these three Boolean expression will be implemented using this simple logic gates in this fashion, because the first expression is a product term a b bar, so which can be getting, these are the inputs line, a and b are the inputs line. So we take a direct to the AND gate, and b let's take by passing it through the NOT gate. So this is the a b bar column, which signifies our x. X means that the a is greater than b. Similarly, for the z is equal to a bar b, so a we pass through a NOT gate, so this is a bar, and this is b, b which we take directly to from the inputs, and so the product term a bar we get, which is z. And the z part, we can say this signifies our a less than b part. And now finally you can see, just as we have told you, that this is an standard XNOR expression. So this XNOR expressions can be written as the complement of XNOR, and we have take advantage of this expression here in this fashion, because at this output we have a b bar, and here we have a bar b. So if we pass these two output into one NOR gate, then we have this expression which is equal to a x NOR b, and which signifies that a is equal to b part. So in this manner we can able to implement our logic diagram for the single bit magnitude comparator. Okay. Now just because of complications in multi-bit magnitude comparator, because as you can see, if we take a value is 4-bit number and b is again 4-bit number, then we have to do the 256 comparison we have to make for writing the x column, y column and z column, in which we are able to recognize that whether a is greater than b, a is equal to b, a less than b or not. So we have taken this concept in this way. This is the multi-bit magnitude comparator, and in this multi-bit magnitude comparator we have a, which is a 4-bit number, b is again a 4-bit number, and these output x, y and z are the comparative comparison result, we can say, of these two numbers, where x is equal to 1, y is equal to 1 and z is equal to 1 signifies a greater than b, a is equal to b, a less than b. So to do so, or to write the output expression, what we have taken, we have write y3 is equal to a3 XNOR with b3, y2 is equal to a2 XNOR with v2, y1 is equal to a1 XNOR with b1, y0 is equal to a0 XNOR with y1, and finally the y is equal to x3 product term y3, y2, y1 and y0, and if this is equal to 1, then we can conclude that a is equal to b. The two number which are 4-bit number we put over here are written like that. And the thirdly x is equal to this a3 b3 bar, y3 a2 b2 bar, y3 y2 a1 b1 bar, y3 y2 y1 a1 b a0 b0 bar signifies the a greater than b and Z is equal to A3 bar B3, Y3 A2 bar B2, Y3 Y2 A1 bar B1, Y3 Y2 Y1 A1 A0 bar B0, which signifies A less than B. So in this case we can able to, with this Boolean expression, we can able to construct the multi-bit magnitude comparator. So thank you. Thank you so much. So we will continue our discussion in for the more combinational circuit design in the coming lecture. Thank you. Hello all. So in the previous video we have discussed the magnitude comparator. We have discussed single bit magnitude comparator, and we also have discussed the multiple magnitude comparator. Now let's take an example of 2-bit magnitude comparator, means how we compare the two numbers which is having 2-bit in each. Okay. So as we have seen, as we have discussed, that now we have two numbers, and these two numbers are A and B. These two numbers A and B are of having 2 digits in each, means let's consider A0 and A1 in A, and similarly B0 and B1 in B in general. So first of all, let's construct a truth table, and by which we actually shuffled two numbers which we can create using these 2 digits, means A0 A1 and B0 B1. So there is a simple way to write all these combinations to compare with each other. Means initially you can do you can consider these A B0 B1 A0 A1 as the 4 different variables, and with the 4 different variables you can generate the 16 combination, and those 16 combination you can write in this way. But yes, of course, these combinations are written for the purpose of comparing the 2 bits number. So this constitute this A0 and A1 column constitutes the 2 bit numbers, and these 2 bits number, if we take the decimal equivalent, will give the magnitude of A, and similarly these 2 digits B0 and B1 together will give the magnitude of B. So based on the 2-digit comparison, we have the 3 outputs, in which first is A greater than B, A is equal to B, A less than B. And whatever the condition is satisfied, we will mark in that specific column, and the remaining thing will put on 0. So similarly, for example, if you look at the first row, in which A0 and A1 is 0 0, which is a decimal if you take the decimal equivalent, then it represents the magnitude 0. And similarly, the B0 and B1 together, if you take, then its magnitude in decimal is equal to 0. Hence what we can say, that A is equal to 0 and B is equal to 0. This is the condition that A is equal to B. Hence we write 1 in this column, A is equal to B, and the remaining thing we put over 0. Similarly, move on to the second row, where the A is 0 1, which is gives the magnitude 0, and B is 0 1, which gives the magnitude 1. So we can conclude that A is less than B. A is less than B. Hence we mark A is less than B column, and remaining two walls are 0. Similarly, the third, if you look at the third, then third magnitude together with A0 and A1 represent 0 magnitude, and here in B it represents 1 0, means 2. Again this A is less than B, so we mark 1 over here, and remaining 2 are 0. In the third row, fourth row, we can say that this is A is 0 0 and this is 1 1. So this is this magnitude of A is 0, and the magnitude of B is 3. So again this A is less than 3, so we mark 1 over here, and remaining 2 are 0. Now in the fifth column, you can see the A is 0 1, its magnitude is 1, and this is 0 0, means magnitude is 0. Here the condition is A is greater than B. So we mark 1 over here, and remaining 2 are 0. So similarly, we do all comparison of 2 digits of A and B, and we mark specific ones in a given these conditions: A greater than B, A is equal to B, and A less than B, in this fashion. And finally we have this is the shortcut representation or the minterm representation of the outputs a greater than b, a is equal to b, and a less than b. So how to write that means, if you look at the column a is greater than b, means where you have these ones, okay, where you have these ones, so against these ones you have to write the minterm, of that specific one. So we can write here like sigma m, this one is correspond to 4, so that's why we write 4 over here. Then this one is correspond to 8, then we write 8 here. This one is correspond to 9, so we write 9. And this one is correspond to 12, m12, so we write 12. This one is correspond to 13, and this is 14, so these are, here we write 13 and 14. And similarly, in the a is equal to b column, we have 1 over here which represents the m0 minterm, so we write 0. Then this is next one is represent 5, m5, so this we write 5. This represents m10, so we represent 10 over here, and this is represents m15, so we write 15 here. Similarly, in the a less than b column, we write 1 for this one, we write 1, m1, this is your m2, this is m3, m6, m7, and m11. So in this fashion, we have get all the three Boolean expression which represents the magnitude comparison of 2-bit numbers. Next, we try to simplify these Boolean expression using the Karnaugh map, that whether we will able to get some reduced Boolean expression or simplified Boolean expression of these three or not. So this first K map we draw for a greater than b and put all these minterms inside the map, inside the K map, and then we try to simplify it. Okay, so we have what we have seen, we have make a group of 4 adjacent cells. This is a quad, two pair are there, means one this one and another is this, by just getting a folding of this K map. So this is the simplified Boolean expression we get after a greater than b. Second, a is equal to Karnaugh K map. For a is equal to b, we map all the minterms inside the K map, but as you can see, we do not get any adjacent cell combination, so no grouping is possible. So we leave it alone as it is here, and we try to get its simplified version using the Boolean algebra. And in the next slide, third K map is for a less than b, in which we again put all the map all the minterms inside the K map, and we can able to make few groups, and the one quad is there and two pair is we can form in this way. So after that we get this simplified Boolean expression in this way. Next, just as we see in the previous slide that a is equal to b, K map is not able to simplify it using the Karnaugh map, so we take the help of Boolean algebra. We take certain variables common, so we'll get this Boolean expression a naught x naught b naught, a1 x naught b naught. So in this manner we get all the three simplified Boolean expression of 2-bit magnitude comparator, in which this expression is for a is equal to b, this is a less than b, and this is a greater than b, and this is a less than b. Now our next task is just to implement the logic diagram of 2-bit magnitude comparator. So we take in the next slide, we take this diagram to implement this diagram. So here we take inputs a naught a1, b naught b1 along with its complement a naught bar, a1 bar, a naught bar, b1 bar, and b naught bar. So with this, as we can see, the expression which we written in the here is a SOP. So with the help of AND OR logic, we can able to implement it. So in the first layer, we can have the OR AND product term, which is going to be implemented using the AND logic, and the final OR gate, which include all the outputs of those AND gates to get the final, to implement the final expression. So in this way, we actually implement our 2-bit magnitude comparator. Means what now, if in this circuit, if we provide any 2-bit number in the terminal a naught and a1, b naught and b1, it will give you the comparison result. If you put some LED kind of element at the output, it will give you the glow according. Okay. So thank you so much. We will continue our discussion for the more combinational circuit in the next videos.